All right, so now that we know the technology that calculus lends us and what we can do with derivatives and integrals, we need to kind of pause and make sure that we understand limits before we move on to derivatives, because we're first going to define derivatives as limits. So naturally, we need to understand limits. Fundamentally, limits are all about how functions behave approaching a certain value, but not necessarily how they behave at that certain value. So let's write that down. We're going to talk about the the approach and not what happens at the value. So we care about the approach, not what happens at the value. And I apologize for my handwriting there. Let's connect the T. Easy enough. So we care about what happens as we approach an x value, not what happens at the x value. So let's jump straight into an example. If we look at the limit of this function that we have here, of f of x, now we say limit as x approaches some number a of f of x. Right? In this case, we see a discontinuity at x equals 2 right here. Right? We know that f of x is defined as x squared for x does not equal 2 and as 5 for x equals 2. So what we care about is behavior as the function approaches x equals 2. So that would be written as the limit as x approaches 2 of f of x. And you may be initially tempted to say that it's 5, right? Because naturally the function is defined as 5 at x equals 2. And that makes a lot of sense. The problem with that is this. We care about the approach, not what happens at the value. So in fact, that is not true. What happens is the closer I get to x equals 2, as I approach the value x equals 2, the closer the function is to y equals 4. But at x equals 2, y equals 5. So in reality, this limit equals 4, but we can define f of 2 as 5. Right? That's the difference between taking the limit as x approaches 2 and finding the value of the function at x equals 2. Okay, that's why we care about the approach with limits and not what happens at the value. This is fundamental to understanding what limits are. So if you don't understand this, pause it, rewatch it, whatever you got to do. But you do need to understand this concept that we care about the approach and not what's happening at the value. Let's jump right into some examples because I think that'll help get out of this kind of theoretical realm of limits, because you may be wondering how to calculate them. So we kind of have three pieces of technology that we can use, or three methods that we can use. The first one being direct substitution. And I'm just going to say direct substitution. And we'll look over an example of that. The second one is factorization. Okay, and the third one is multiplying by something called the conjugate. So example number 1, we're going to look at the limit as x approaches 3 of x minus 2 over x plus 2. Now, direct substitution says that we can take this value right here and simply plug it in for our x values. So if we do that, we get 3 minus 2 over 3 plus 2 and find that the function approaches 1/5. Now, the second method is factorization, and it's a little bit more complicated, but it ends up being pretty straightforward. So the limit as x approaches 2 of x squared minus 4 over x squared minus x minus 6. Now, if we tried direct substitution, this is what we'd get. We'd get 4 minus 4 on the top, which is 0. Right, so it's looking good so far. And if we do it on the bottom, we get 4 minus 2 minus 6. We get 4 plus 2 minus 6, which is also 0, right? Excuse me for that bad example. So this turns into something we like to call the indeterminate form. Indeterminate. And what that means is, generally, when you get the indeterminate form, you need to manipulate your f of x in order to make taking the limit more simple. So what we're going to do here, because method number 2 is factorization, is factor. So we're going to factor this as x plus 2 times x minus 2 over x plus 3 times x minus 2. And we're going to take the limit as x approaches 2. Okay? And what's really interesting here is you should see immediately that this term and this term cancel each other out. So now you're left with something really similar to our first example, which is just a simple direct substitution problem, and you end up with the answer 4/5. Now the third and final example I wanted to go over is multiplying by the conjugate. Now this is a pretty dirty way of taking the limit, but sometimes it's necessary. So let's write down our problem and you'll see what I'm getting at. The limit as t approaches 0 of t plus 4 square rooted minus 2 over t. Now this is a weird problem. When we do direct substitution, we get square root of 4 minus 2, we get 0 over 0, which means we're indeterminate and we need to manipulate. Now, we said we wanted to multiply by this thing called the conjugate. And it's difficult to explain, but it's easy to see what it is. So I'm going to write it out, and then we're going to talk about it. So we're going to multiply by the conjugate, t plus 4 square rooted plus 2 over itself. T plus 4 square rooted plus 2. And this should be a big multiplication sign, right? So we're going to multiply by the conjugate. What we did was we took this sign, flipped it, and then multiplied it by the conjugate over itself, basically. So we're not changing the value of the function at all. What happens here is pretty interesting. When you multiply all of this out, you get t plus 4 minus 4 over t times root t plus 4 plus 2, right? And of course, the limit as t approaches 0 of this, right? What's interesting is this 4 and this 4 cancel. Then you're left with a t on top and a t on the bottom that can cancel. And you're left with a really easy limit. The limit as t approaches 0 of 1 over the square root of t plus 4 plus 2, which by direct substitution will give you 1/4. That's pretty straightforward. And what you should see is kind of a pattern. We're using these methods over here, direct substitution not so much, but factorization and multiplying by the conjugate to manipulate our functions here and here in order to use a really simple method called direct substitution.